Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the Maxwell relations. For a function that depends on two variables, such as z equals z, x, y, we have obtained the fundamental relation for the total differential of a dependent variable in terms of its partial derivatives with respect to the independent variables. Variables x and y are called natural variables, and m and n are called conjugate variables. We learned the order of differentiation is immaterial for properties since they are continuous point functions and have exact differentials, or the differential order could be interchanged for smooth functions without changing the results. For thermodynamic energy functions of U, H, F, and G, we have the exact differentials known as Gibbs equations. From the first Gibbs equation we have, since the order of differentiation is immaterial for properties we have, this expression indicates that the change in temperature that occurs when volume changes while entropy remains constant is identical to the absolute change in pressure that occurs when entropy changes while volume remains constant. From the other three Gibbs equations, we have the other three expressions. These relations are the Maxwell relations and are applicable to thermodynamic state functions and equilibrium. From the Gibbs equations, the conjugate variables are, and we then have four additional property relations. Since the order of differentiation is immaterial for properties, we then have Maxwell relations. The Maxwell relations are extremely valuable in thermodynamics because they provide a means of determining the change in entropy, which cannot be measured directly by simply measuring the changes in properties P, V, and T. Note that the Maxwell relations given above are limited to simple compressible systems. However, other similar relations can be written just as easily for non-simple systems, such as those involving electrical, magnetic, and other effects. In the previous work, we derived the differential forms of the state functions U, H, F, G, and their corresponding natural and conjugate variables. We summarize these relations for ease of reference in the table. We observed that all thermodynamic state functions listed in the table are a function of four independent variables in total, either as their corresponding natural or conjugate variables. For example, for the differential form of internal energy U is V, we have its conjugate variables appearing as the coefficients of differentials of its natural variables. This symmetry appears in the relations for the remaining functions as well. In addition, and from a physical point of view, experimental measurements of variables t, p, v are more easily accessible than s. This motivates seeking relations that can eliminate the need for measurement of s. The solution comes from Maxwell relations, which make use of this symmetry and the total differential properties of the thermodynamic function to derive relations among the natural and conjugate variables themselves. We present a procedure to recall Maxwell relations using the definition of a determinant of a matrix with having the differential relations for a desired thermodynamic function for which we seek the corresponding Maxwell relations. The procedure is as follows. We build a matrix consisting of the function and its natural and conjugate variables, and let the determinant of such matrix be equal to 0. The procedure is shown in the figure. For example, we use the suggested procedure for Gibbs function having natural 1 equals t, natural 2 equals p, conjugate 1 equals minus s, and conjugate 2 equals v. Therefore, we have. This gives the relation as expected. For reference, we list all the Maxwell relations in the table. Pay particular attention to the natural variables and the conjugate variables in the construction curl structure in the table. Okay, that's all for this task. Thank you very much and see you next time.